Welcome to the Strategic Energy Group Building Operator Smart Series. In this video, I'm going to help you find the right balance for building pressure strategies. For additional energy saving tips for your buildings, please subscribe to our YouTube channel by clicking on the subscribe button. My name is Dusty Farrell and I'm an energy coach with Strategic Energy Group. And like previously stated, and by now I hope you have them memorized, these are the 4 common opportunities found for reducing energy in commercial buildings. Number 1, equipment scheduling. Number 2, appropriate use of outside air. Number 3, simultaneous heating and cooling. And the last, sensor air. If you joined me in the previous 2 videos, I went over the 3 primary reasons for using outside air in our buildings. If you'll recall, the first one was free cooling, the second one, ventilation and indoor air quality, and the third primary reason for using outside air in our building is for controlling building pressure. This is what I'll be discussing with you today, so let's get started. While commonly overlooked and oftentimes misunderstood, proper building pressurization is not only vital to the health of a building, but also plays a significant part in energy management. There's some good news here is that incorrect building pressure is very easy to recognize. Just like when you feel a blast of air rushing at you or behind you when you are exiting an exterior door of a building. And when this happens to you, do you ever wonder why and think, man, this building is too positive or it's way too negative in pressure? Questioning this building pressure imbalance and taking action is what I hope to instill in you from this video, because the negative effects from this type of condition typically has an energy penalty associated with it. Okay, so what is so important about building pressurization? Well, generally, commercial buildings are designed to maintain a slight positive pressure anytime your fan systems are in operation. And the reason for this is to minimize the infiltration of unconditioned outside air, which can be dirty and is responsible for many cold and drafty complaints. But even more importantly, and did you know, a slight building pressure is needed to discourage the infiltration of moisture into the building's envelope, where it can collect and cause damage. In the case of this ugly water-stained ceiling tile, the building was constantly in a negative pressure and managed to pull rainwater through a tiny opening at the base of a roof-mounted exhaust fan, and ultimately the rainwater deposited above the restroom ceiling tile. This is not good. So how we control building pressure is accomplished through a number of methods and is a bit of a balancing act. But the takeaway for you building operators is to always recognize and maintain a slight positive building pressure anytime your fan systems are in operation. But maintaining a balance of building pressure will be challenging unless we have a thorough understanding of how the building and the fan systems were designed to control this pressure. To make matters even more interesting, you're going to love this one. The controlling strategy for building pressure will vary from one building to the next. So this is not a one-size-fits-all. But what's important here is that you have a working knowledge of the building mechanical system's sequence of operation. That way, you'll easily recognize the signs and symptoms of building pressure imbalances. Now, I'll share the symptoms in a moment, but first, let's cover a common building pressure sensing device that's likely installed in your building for controlling pressure. At its basic, a building static pressure sensor is used to measure and provide feedback to the building automation system, or the BAS. And it accomplishes this by comparing the pressure difference between the indoors and the outdoors. And if you don't know the location of your building static pressure sensor, I encourage you to refer to your BAS installation documentation and or the as-built drawings. Now that we have the actual building pressure, let's cover how it's controlled. With the fan system operating, the pressure sensing device provides feedback to the BAS, where the feedback value is going to be compared to a set point. For an office building, you'll typically find the set point between 0.03 to 0.05 inches of water gauge, but that's going to vary according to the building space use, type, and the building. Once the building pressure exceeds that set point, the BAS will begin to systematically reduce the building pressure through a number of methods. These could include commanding relief dampers to open farther, or turning on an exhaust fan, or for precise control, slightly speed up an exhaust fan by means of a variable frequency drive. And this same strategy works in reverse. To increase pressure, it will reduce the damper position or possibly slow the exhaust fan speed down. This is a dynamic operation that you won't even know is occurring until a pressure imbalance occurs, and then some of the signs begin to show up. Now, I mentioned building pressure imbalance, and I want to make sure we all understand what I'm referring to. This is caused by a disproportionate amount of outside air coming in the building versus the amount of air that's going out. So, for an overly pressurized building, some symptoms for you to be on the lookout for are a blast of air in your face when you're opening exterior doors as you walk in. Sometimes you can even hear air whistling around the doors opening. Or exterior doors that are unable to close and simply are just hanging open. In this infrared image, you can easily see excessive building pressure forcing warm air out of the gable ends that's represented by the brighter colors. In this example, we are practically heating the outdoors and is a big energy penalty. For negative building pressure symptoms, I want you to be on the lookout for these telltale signs. Okay, I know you're not going to have frost actually in the building, but you get the idea when I call this one the cold lobby syndrome. Cold lobby syndrome is a condition when the cold outside air is sucked in and around your exterior lobby doors that often necessitates a much earlier start time for the heating systems to get the place warmed up. In this infrared image of an exterior door, the darker color at the base of the door, do you see that? This represents cold outdoor air literally being sucked into the building because of the building's excessive negative pressure. In this case, we discovered that the exhaust fans were allowed to operate overnight when the primary fan systems were scheduled off. Now, something to note here is that the energy penalty for negative building pressure is twofold. One, electric energy increase by allowing the exhaust fans to operate all night in an otherwise unoccupied building that caused an earlier start time of the primary fan systems. And two, the gas energy increase to reheat the cold air that was sucked in overnight. Here's a final few building pressure tips for you to remember. When your primary fan systems are operating, always maintain a slight positive building pressure between 0.01 at least to 0.05 inches of water gauge. Remember, better positive than negative. I want you to learn to recognize the common symptoms that are associated with excessive building pressure and negative building pressure. Remember, building pressure imbalance is caused by disproportionate amounts of outside air coming in the building versus the amount of air going out. And the last tip, if the building is equipped with a building pressure sensor, I challenge you building operators to periodically review and scrutinize several weeks of trend data. I want you to ensure that your building pressure is slightly positive during the operating hours and does not go negative after hours. Now that you have joined me in these last 3 videos and are so well versed on the appropriate use of outside air, I'd like for you to follow me a little bit further on a virtual service call. I'm going to set the stage by saying that I get a work order for a too cold comfort complaint. You know, "Brr, it's freezing at my desk, call in a work order." Or maybe the lobby doors won't close, or possibly the energy champion is investigating why the gas usage has gone up considerably. Being a seasoned building operator, I suspect that there is an issue with an economizer damper on one of the main rooftop units. And here I sit now before my building automation system's computer, ready to investigate. The first thing I do is I check the return air temperature of 69 degrees, and this seems okay. And then I check the position of the outside air damper, and I can see that it's commanded to 10% open. So far, so good. Then check the supply air temperature of 52 degrees that's being provided to the building, and I know this is a bit too cold, especially with an outdoor air temperature of 48 degrees and a mixed air of 52. Are you following me? Then I compare the return air and supply air temperatures, and I realize there's a 17-degree difference between the two. Why is the supply air temperature so much colder than the return air when outside air damper is commanded only 10% open? Utilizing the percent of outside air calculation from video 4, I easily calculate the system is actually drawing nearly 80% of outside air. So, armed with this knowledge, I decide it's time to head up to the roof to perform a visual check of the outside air damper in this rooftop unit and verify if it's actually open farther than the displayed 10%. Okay, so we earlier suspected, looking at the BAS graphics, that our outside air damper was actually open more than 10%. So we went up to the unit, we opened up the mixed air compartment, and we're getting a good look at what's going on here, and it was pretty obvious what we found. Before I get into that, let's talk a little about what's going on in this compartment. Right here we have the actuator motor. This actuator motor, controlled by the BAS, drives this rod right here, and this is the return air dampers. This is also, the outside air dampers are also driven off of this. That's the outside air damper back there. It is about 50% to 75% open. Now these two dampers need to work together. Return air is wide open, so therefore that outside air damper right now should be pretty much 100% closed. When we dig in this thing, we can see that this connecting rod right here had come loose. It's connected commonly to this actuator motor here that I spoke about earlier. So we look around the compartment, sure enough we can see that there's a set screw for the nut and bolt had come loose, and it's just basically laying here at the bottom. Kind of laying right down in there. So this is a pretty obvious fix and easy to do. We'll put the set screw back in place. We will re-index everything, and then we'll put this economizer through a full functional checkout to make sure our repair is good to go. Now that the linkage for the outside air damper has been repaired, I go back down and I check the BAS screen once again and can now confidently see that the temperature difference between the return air and the supply air is 3 degrees. So with that, I can close out the work order and report to the energy champion the cause of the sudden gas increase. This concludes video 5 of this 8-part series. Again, I hope the information reinforces what you already know and enlightens you to a better understanding of building opportunity assessment. In part 6 of the next video, keep learning, as my very smart friend Steve is going to cover energy waste from simultaneous heating and cooling. And one last time, for additional energy saving tips for your buildings, please subscribe to our YouTube channel by clicking on the subscribe button.